Okie doke. Well, welcome back to spring semester. We survived the winter onslaught of way too far below zero temperatures. So we know it's got to get warm soon because, after all, it's spring semester. We're going to start off with our mini lectures in Chapter 14, which is kind of a nice recall, review, revisiting of molecular orbital stuff. So let's get started. It's all orbitals, as I've said before, and we'll say again. But what we're learning in Chapter 14 is things are never quite as simple as they seem. We've learned a little bit about delocalization, but now we move on to this concept of something called multiple center molecular orbitals. What this is basically doing is trying to tie together the concept of delocalization, as we've seen in resonance, with valence bond theory, molecular orbital theory. The focus in this chapter is primarily on two concepts, conjugation and aromaticity, and the reason is because it explains things. So, for example, we saw in first semester that conjugated alkenes, conjugated dienes, can undergo both 1,2 and 1,4 addition. And we kind of tried to explain that by virtue of resonance delocalization. But it's really kind of a hard concept to wrap your head around when it comes to really nailing what's going on. Another example is the one shown here. I mean, if a conjugated diene would undergo this kind of addition, why wouldn't this conjugated triene? Well, this is an aromatic ring, benzene, and we will see in this chapter that aromatic rings are unusual in their lack of reactivity, and we'll discuss aromaticity in even greater detail a little bit later on in the semester. So as usual, we're learning taking this new, deeper look at molecular orbitals so that we can understand and predict the properties and reactivity of these molecules. And, as usual, it's all orbitals. Alright, so valence bond theory revisited. In the beginning, back when we were brand new in O-Chem 1, we found out that Lewis structures really were too simplified. Resonance was introduced. That helped quite a bit. It helps explain a lot, but it still is not adequate, nor is our current understanding of molecular orbitals. We're going to illustrate this by looking at two examples, the first of which is the Allyl cation. So the Allyl cation, of course, is this guy, where you have a positively charged sp2 hybridized orbital, carbon, with a positive charge, empty p orbital, right next door to the alkene. So this is the Allyl cation, and if we try to represent the molecular orbitals for this, we get into a mess. Yes, we know that by resonance we can say that, yeah, hey there, we know these are delocalized, etc., etc. But how do you draw that with molecular orbitals? Well, okay, so sure, there's a pi molecular orbital here, and an empty p orbital here, and that sloshes over somehow. Hey, Awatha, things just go to pieces. Doesn't make a whole heck of a lot of sense. How do I figure out what the hybrid molecular orbital looks like? How do I know what the HOMO is? Which is the LUMO? How do I pull this all together? Well, we pull it together by introducing the concept of these multiple center molecular orbitals. The Allyl cation has 16 electrons total. 2, 4, 6, 8, 10, 12, 14, 16. But we're only interested in those valence electrons that are where the chemistry takes place. So that means we're focusing strictly on the p-pi system. So we're only interested in the pi electrons here that are delocalized between the p orbital and the p orbitals, the pi molecular orbital, here on those two carbons. But how do we really explain this? How do we understand the molecular orbital picture for some kind of system like this? Well, we rely on the basics that we've already learned. Go back to the basics and recall that when we're looking at molecular orbitals, the number of molecular orbitals has to remain the same as the number of atomic orbitals. So in this system, we're talking about 1, 2, 3 p orbitals. Therefore, we're talking about 3 molecular orbitals. 3 atomic orbitals, 3 molecular orbitals. Critical to the understanding and construction of molecular orbital diagrams is knowing that the molecular orbitals must be symmetric. So it is a given that whatever molecular orbitals we come up with, the electron density must be symmetrically distributed across the system. A corollary to this is that as the molecular orbitals build up in energy, the number of nodes in each molecular orbital will increase. So we start with 0 nodes, that's the lowest energy, 1 node, slightly higher in energy, and so on and so forth. Then when we have completely constructed the molecular orbitals that make up our system, we can take the electrons that we know are part of the system and fill our molecular orbitals from low energy to high energy, and then ascertain what is our HOMO, the highest occupied molecular orbital, what is the LUMO. And you recall from that kind of information we can predict how a reaction will take place. Alright, so let's look at this. How do I construct the molecular orbital diagram for the allyl cation? Well, we have 3 atomic orbitals, 3 p orbitals. So 9 times out of 10 books don't show anything here at this node. Just keep in mind that that's the nucleus of the atom. So I have 3 p orbitals on 3 adjacent carbon atoms. So the molecular orbital with the fewest nodes would of course be the one that is fully bonding. So all 3 atomic orbitals would be in phase. They would overlap nicely to make a completely symmetric, evenly distributed molecular orbital. And there's my picture of it. Gaussian has a much better picture of it, as shown here, illustrating the symmetry and illustrating the beautiful distribution of electron density, fully symmetric on the top face and the bottom face of this molecular orbital. There's a nodal plane, but otherwise there's no nodes in that molecular orbital. So this molecular orbital is known as pi 1. It's going to be pretty easy to figure out what pi 3 looks like too. But what about the next higher energy? So this has 0 nodes. How can I come up with a symmetric molecular orbital that has only 1 node? Because if I try something like this, well, there's only 1 node, but that's not symmetric. So that's not going to work. Well, the way we make it work, oddly enough, is by saying that, gee whiz, that middle carbon, it doesn't even have an orbital. So if we look at Gaussian again, here is a nice representation of that particular molecular orbital. You can see the p orbital on each terminal carbon, but this middle carbon has no orbital on it whatsoever. So there's very clearly a node. but the molecular orbital itself consists of just these two terminal p orbitals. Pretty funky. All right, well then the third molecular orbital, this would be pi 2, and it has the one node. The third molecular orbital then must be the highest energy two-node system. That guy's kind of off the mark there. So, by having all three p orbitals completely out of phase, we have two nodes, one node, no nodes. We know that our system has two electrons, so they go in the lowest energy pi 1 molecular orbital, and this is the entire molecular orbital picture for the allyl cation. What does this explain? Well, it pretty much explains everything, in that if you look at pi 2, you can see why there would be a reactive termini at each end of the allyl cation, because there's going to be an equal amount of, I'll say electron paucity. I basically mean we got a seriously electrophilic carbon here because the empty p orbitals, and they're evenly distributed on each terminus. The perfectly delocalized psi 1 explains why for an allylic system everything is in the plane so that I can have complete delocalization across all three carbons. In other words, we don't see rotation like so to put the p orbital 90 degrees to these, because then I couldn't have my delocalization. So that's this picture of the allylic cation, and what we'll look at in the next mini lecture is the 1,3-butadiene system, which can be extrapolated to just about any conjugated alkene system that you want to. But before we do that, a good thing for you to contemplate next, that's the one I want to do, is to simply, that is what I want to do, but I want to get back to here. Show you the picture of the pi 3 fully antibonding orbital, so you can see nice node there, nice node there. That's what pi 3 looks like according to Gaussian. But at this stage, what you want to do is ask yourself, can you now do this same sort of mental exercise for the allyl anion? So for the allyl anion, we'd be talking about this kind of system. Aha! Where the only thing that's changed now is the number of electrons. The allyl radical, same deal. Different number of electrons. What is this going to change? It's going to change which one is the HOMO and which one is the LUMO. This is the highest energy occupied molecular orbital for the allyl cation, and this is the lowest unoccupied molecular orbital for the allyl cation. Remembering that reactions take place by interaction of the HOMO of one species with the LUMO of another. Terribly important that we know how to identify the HOMO and LUMO. Okay, so that's it for this mini lecture, and we'll move on to butadiene.